right, guys, let's continue. All right. So we're talking about mechanisms of cell injury. All right. All right. So we're talking about mechanisms of cell injury, and the first that we're going to talk about is hypoxic injury. So this is when oxygen delivery to the tissue is reduced, and we actually know quite a lot about what happens to cells when they become hypoxic, and much of what we know. What's going on? Much of what we know about hypoxia has been learned from studying myocardial infarction and hypoxia of cardiac muscle cells when blood flow is reduced during either ischemic events or in the context of infarction. So if we look at the next slide here, what we see is a typical ischemic/hypoxic event where at the very top here on the left, under reversible cell injury, we see obstruction or cessation of blood flow and ischemia. Okay? Now, when this happens, we have less oxygen delivered to the mitochondria, which means that we have less ATP production. Okay? Now, when that happens, there's a few things that results from this. First off, when we can't, when aerobic metabolism shuts down, glycolysis actually increases in rate, right, to compensate and produce ATP. But the product of glycolysis, or a byproduct of glycolysis, is lactic acid, which is going to cause the cell to become acidic. Okay. And acute cell acidity, or the drop in pH, is going to lead to damage of intracellular contents. Okay, so we see nuclear chromatin clumping of proteins like the proteins around the chromatin. We see swelling of the lysosome. Now, the lysosome is an organelle in the cell that carries out intracellular digestion. So it's got a lot of digestive enzymes. Now, when the lysosome swells and bursts, those digestive enzymes spill out into the cell, and basically what we get is autodigestion, where the cell digests itself. Okay? Now, once those lysosomes do that, now we're at a one-way road to necrosis. The cells are not going to recover from that. If we look at the other end of that drop in ATP, we see that we get a decrease in the activity of those sodium pumps. Okay, so the sodium-potassium pumps stop working because we don't have ATP to run them. Intracellular sodium goes up, extracellular potassium goes up, intracellular calcium goes up. And the cell starts to accumulate water, and you get this acute cellular swelling. And when the cell swells, the next thing that's going to happen is that all of the organelles are going to swell. Okay? And when the organelles start to swell, like the endoplasmic reticulum, when it starts to swell, ribosomes start to detach. Okay. When the mitochondria starts to swell, those folds within the mitochondria that where the electron transport chain is located, they start to break down. And again, these are points of no return. Okay? When we start to get organelle swelling, that cell is well on its way to dying. Okay? So hypoxic injury will cause cell injury and reversible cell injury fairly quickly. Okay? And it's pretty easy to see the hypoxic cells because they will be bloated and swollen, okay, from this fluid accumulation. So another source of cell injury, a very, very common source of cell injury, is injury by exposure to reactive oxygen species. Okay? So we're used to oxygen existing in that O2, okay? Two atoms of oxygen double bonded together. Okay? And this is a very stable molecule. There's no unpaired outer shell electrons, okay? So this is the non-reactive oxygen species. And the rest, superoxide anion, peroxide, hydroxyl radical, right, hydroxyl ion, these have an unpaired electron in their outermost shell and cause damage because they will steal an electron by breaking bonds that they come in contact with. And the damage that's caused by these reactive oxygen species, I mentioned earlier, lipid peroxidation. Okay? Lipid peroxidation is going to cause rigidity of the plasma membrane. Okay? Disruption of proteins can also affect membrane-bound enzymes and other receptors and proteins on the cell. It can change the permeability of the cell. And then we also see DNA damage, okay, and potential mutagenesis. Now, reactive oxygen species, the major source of reactive oxygen species in the body is metabolism. Okay. Anytime we metabolize food, we are producing reactive oxygen species. Okay? If you are alive in this country, it's hard to not hear about how good antioxidants are and foods that are high in antioxidants and that kind of thing. So the reason why antioxidants are beneficial are because they have the ability to neutralize these reactive oxygen species. An antioxidant is a species that neutralizes a radical, a free radical. Okay. There's a little bit of a digression, but if you have ever read about the anti-aging science, the science of anti-aging, which of course in this country is very, very popular, there's actually only been found to be one clearly effective way to increase somebody's the length of somebody's life and prevent aging, and that is a severely caloric restriction diet, right? Severe caloric restriction. We're not talking about like shaving a couple hundred calories off of your diet. We're talking about caloric diets that are like 500 and 600 calories a day. Now, it's not a fun way to live, but the way that it works, the reason why it actually works is because it reduces the production of reactive oxygen species. by reducing metabolism. So that's thought to be the major mechanism why this severe caloric restriction works. There are other ways that it harms your body. I'm not advocating for it in any way, shape, or form, as I am evidence of. I do not recommend it, but just in terms of the science, it does seem to lengthen people's lives because of this reduced metabolism. Okay, but there are other sources of reactive oxygen species. Okay, exposure to UV light, ionizing radiation, smoking, air pollution, okay, and very importantly, inflammation. Okay, inflammatory cells like neutrophils and macrophages, when they take part in acute inflammation, they release reactive oxygen species. Okay, and it's part of what makes inflammation a damaging process. Okay, but it's a little like debriding a wound, where we cause some damage in order to clear the wound and set up the stage for clean repair. Okay, so reactive oxygen species occur naturally in the body, and then they can also be caused by the exposure to harmful sources that cause injury. Okay. Okay. So when tissue or cells are under stress or persistent injury, they will adapt in order to maintain survival and maintain integrity of the tissue. Okay? And some of these forms of adaptations involve a morphological change in the tissue or a physical structural change in the tissue. So some examples of this include atrophy. So atrophy, compared to normal, atrophy of tissue means that you get a reduction in cell size and function. Okay? You get a reduction in cell size and function. The opposite of atrophy is hypertrophy. You get an increase in cell size and function. But what's important about atrophy and hypertrophy is generally the number of cells are staying the same. With hyperplasia, the cell size has not changed, but the cell number has increased. Okay? So hyperplasia is an increase in cell number, but not an increase in size. Now, oftentimes, hypertrophy and hyperplasia will happen together in a tissue. And we'll get to that. Another common manifestation of cell injury or adaptation is metaplasia. Now, metaplasia happens in tissue that is actively dividing and replacing itself. Okay? And an example of where we see metaplasia is in epithelial tissue. Because epithelial tissue throughout our body is constantly renewed. So with metaplasia, the normal structure of this tissue changes. The cell type that's found is changes. Okay, and I'll elaborate on that, and we'll look at an example of this. And then dysplasia is not adaptive. This is the one change that is not adaptive, but rather a manifestation of injury. Okay. And with dysplasia, you get a derangement of the control over cell division and cell structure in a tissue. Okay. And oftentimes dysplasia is considered precancerous and neoplastic. Okay. Okay, so let's talk a little bit about atrophy. So, atrophy of tissue, as I said, it means that cell number has not changed, but cell size and function has decreased, right? Functional capacity and size has decreased. Now, atrophy, for almost all of these adaptations, they can fall into two categories. There's something called physiological atrophy, and then there's something called pathological atrophy. Okay? Physiological atrophy means that it's a normal part of the function of the tissue or the development of the tissue. Okay? And physiological atrophy happens during either embryological and fetal development or in early infant and childhood life. Okay? And what happens is, oftentimes when, especially like the central nervous system, will have more cells than we need, right? Or more, a cell will have more branching than it needs, and then it'll decrease in size based on what branches get reinforced and what structure gets reinforced by use. Okay, and so that paring down of size is that physiological atrophy of development. Pathological atrophy tends to happen because of two causes. Either a decreased functional demand or a decrease in growth stimulation. A decrease in growth stimulation. So, decrease in functional demand. An example of this is disuse atrophy, and it's probably the form of atrophy that we all have an example in our mind about. Okay, so you break your arm or you break your leg, it gets casted. You stop using it for 6 weeks, 2 months, and then when they take the cast off, the arm is very small or the leg is very skinny and it's very weak, right? So the muscles have shrunk because of disuse, because of decreased functional demand. And we all know that that's a reversible change, because as soon as we slowly increase the functional demand, those cells will rebound in size and function. Okay. Atrophy that's caused by decreased growth stimulation, one that's easy to understand is what actually a picture that I have up right here. That we've got on the upper picture, we've got a picture of liver tissue that is normal. And then on the bottom in the purple, we've got atrophied liver tissue as a result of basically malnutrition. Okay. So the growth stimulation is coming from calories and protein. And in the absence of that, the cells atrophy. Okay. And you can see one way to notice the atrophy in the picture is just notice that there's a lot more white space in the picture with the purple cells. right? And that white space is spaces in between the cells because the cells have gotten smaller. Another common growth stimulator that, when decreased, can cause atrophy is hormonal stimulation. Okay. So in the absence, there are times where hormone levels pathologically drop, or the production of the hormones drop, and the tissue that is reliant on that hormone for growth will atrophy. An example, I was hoping you wouldn't ask that. Example's not coming to mind. What's that? Prolactin dropping, yeah, that's a good one. I don't know why I didn't think of that one. Yeah, so when prolactin levels rise during pregnancy and then postpartum, there's an elaboration of breast tissue, and then when you stop breastfeeding, the prolactin levels drop and the breast tissue decreases in size. That's a very good one. Okay. Okay. The opposite of atrophy is hypertrophy. And with hypertrophy, we don't get an increase in cell number, but we get an increase in cell size. Okay? What we're looking at here in this picture is myocardial hypertrophy. And specifically, this is a left ventricular hypertrophy, meaning that the muscle of the left ventricular wall has increased in size and thickness. Okay? And if you notice, it has decreased the chamber size. Okay? Now, this kind of hypertrophy, left ventricular hypertrophy, is caused by an increase in functional demand. Okay? One example of something that can cause this is actually hypertension. So having high arterial blood pressure causes your left ventricle, to pump harder in order to eject blood into the arterial system, and that causes hypertrophy. Okay. So with hypertrophy, like atrophy, we have physiological hypertrophy and pathological hypertrophy. Okay? And physiological and pathological hypertrophy have actually the same causes, just one is normal and one is not. Okay? And the causes are, not surprisingly, the opposite to atrophy: increased functional demand or increased growth stimulator. Yes, for both, physiological and pathological. Increased functional demand and increased growth stimulator. Okay. On the physiological normal side, the whole purpose of strength training, right, is to cause hypertrophy of skeletal muscle. Right? Increased functional demand, that's a physiological hypertrophy. That is a normal, healthy hypertrophy. Okay. This kind of hypertrophy that we see with the cardiac muscle, the increased functional demand is a pathological increase in functional demand. Okay? And so it creates a pathological hypertrophy. Okay? Now, on the increased growth stimulator, again, hormonal stimulation is a really good example. Okay? During puberty, during pregnancy, we get an increase in hormone production and an increase in a hypertrophy of tissue. Okay? That's physiological. if someone has a benign tumor that overproduces hormone, right, they can end up with hypertrophy of tissue that's pathological. Make sense? So both forms of hypertrophy really have the same cause. It's just one is appropriate and one is pathological. Okay? Increased functional demand and increased growth stimulator. Hyperplasia involves an increase in cell number. Okay? Increase in cell number. The hyperplasia and hypertrophy often happen together because, again, they have the same forms of stimulation. Okay. And again, we also see physiological hypertrophy, hyperplasia and pathological hyperplasia. Okay. So increased functional demand and increased growth stimulator is also going to trigger hyperplasia. Another cause of hyperplasia is also persistent injury, depending on the tissue type. So the picture that we have here in this slide, the picture in A is normal epidermal tissue, right? So you see the surface epidermal tissue in dark purple. And then in the B picture, we have hypodermal hyperplasia as a result of psoriasis. Right? In psoriasis, we've got a persistent inflammatory injury to the skin causing hyperplasia of the epidermis. Okay. Now, if we go back to myocardial hypertrophy, increased functional demand can cause hyperplasia as well, but we never see cardiac hyperplasia. Why? Anybody know? They are non-dividing cells. That's right. Cardiac muscle is not, they are non-dividing cells. Okay? So there are tissue types where we will only see hypertrophy and not hyperplasia because those cells can't multiply. Okay? But if the tissue, the cells can multiply, an increased functional demand will often produce both hypertrophy and hyperplasia. Okay? Okay. Questions about that? We're all good? Mm-hmm. That's right. That's right. Okay. Now, the story with metaplasia and dysplasia. When we talk about metaplasia and dysplasia, now we're talking about tissue types, like I said, that where we have constant turnover of cells. Okay, with epithelial tissue is constantly being replaced. Okay? And the process of replacing epithelial tissue is a process that involves both cell division and something called cell differentiation. Okay? And cell differentiation means that a cell moves from one cell type that is less mature to another cell type that is more mature. Okay? And you can have multiple differentiation steps that are going to be between the tissue stem cells and what we call the terminally differentiated cell. Yeah. So with cell differentiation, the cell is moving from a less mature cell type to a more mature cell type. So we start off with some kind of tissue level stem cell, right? One of those adult stem cells that are not controversial. All right? A tissue level stem cell. And this stem cell is going to undergo both cell division and cell differentiation. Okay? It's gonna make copies of itself, but it's also going to form, I'll call this D1, meaning the first differentiation step. Okay? And let's say that there's several differentiation steps. D2, and then finally D, I'm going to put T, because this is the terminally differentiated cell. This is the cell that there's no more steps beyond that. Okay? When you look at epithelial tissue, this cell is what you're supposed to see, the terminally differentiated cell. This cell has two important characteristics. Okay? This cell no longer divides. Okay? It no longer divides. And this cell is functionally mature. Okay? So the terminally differentiated cell is the fully functionally mature cell, and it also can't divide anymore, which means that when this guy dies, he's just replaced by another cell. Okay? And this is what I mean by there's constant turnover. This guy is constantly being born, dying, and getting replaced. Okay? Now, let's take a tissue type where we see this kind of growth. The epithelial cells that line the airways. Okay? The epithelial cells that line the airways, when we look at them, they are what we call columnar ciliated epithelial tissue. Okay, columnar ciliated, meaning that they are made up of a single layer of cells that look like tall columns, and they have cilia facing the interior of the airway tube. Okay, and the cilia is designed to move mucus out of the airway. Okay? Now, in order to get to, so the ciliated columnar is the terminally differentiated cell type. There are less mature cell types that happen before you get to the terminally differentiated cell. With metaplasia, metaplasia happens as a result of persistent injury to the tissue. And what you get is, instead of seeing the terminally differentiated cell, you will see a less differentiated cell type replacing it. Yeah. So metaplasia is a result of persistent injury to the tissue, and it involves the replacement of the terminally differentiated cell with an earlier, less differentiated cell type. So it's not uncommon for chronic smokers with that persistent injury of smoking to see metaplasia of the respiratory airways, where instead of the columnar ciliated cells, you get what's called simple squamous. Simple squamous cells, if you've ever done that thing where you scratch the inside of your cheek and you plate it on a microscope, right? Simple squamous cells are those really flat epithelial tissue. Okay. This replacement of the ciliated columnar with simple squamous, this is metaplasia. And the purpose of metaplasia is that by having the tissue be replaced by a less differentiated cell type, this cell type has more mitotic activity. It can divide and can sustain better this persistent injury. Okay. But what's the consequence? It's less functional, right? The simple squamous is less functional in that airway than the ciliated columnar. Okay? Simple squamous don't have cilia. So you have a very difficult time clearing that respiratory mucus, okay? Which contributes to that classic smoker's cough, right? So if the cilia can't move the mucus up, you got to cough to help get it up, okay? Now, metaplasia is completely reversible. You take away the smoking, you take away the persistent injury, and the tissue will revert back to, won't take too long for the tissue to revert back to the normal terminally differentiated cell, okay? But metaplasia is also thought to be, to increase likelihood of movement towards dysplasia and cancer. Okay? Especially if the source of the injury that causes the metaplasia also can cause mutagenesis or carcinogenesis, okay? Which cigarette smoke does. Another example of metaplasia that we see is people with Gerd. So people with gastroesophageal reflux disorder, where they constantly have reflux, they are more vulnerable to what's called Gerd's esophagus, which is a metaplasia replacement of the esophageal epithelium. And Gerd's esophagus increases someone's likelihood of esophageal cancer. Okay? So metaplasia is adaptive. It's trying to adapt to this persistent injury, but it reduces the function of the tissue, and it increases the likelihood of mutagenesis and cancer. Dysplasia, on the other hand, now if you look at this slide where it has dysplasia and compare it to the metaplasia, you should see a couple of things. The first thing you should see is the tissue with dysplasia, the cells are greater in number, right? They're climbing on top of each other. They don't have a uniform appearance. Some are small, some are big. And some of the cells are in active mitosis, right? All of those characteristics, high cellularity, irregular cell shapes, high mitotic activity, this is malignant tissue. Okay. So dysplasia happens when the normal controls over cell division and differentiation become abnormal. And the tissue overproduces cells. The cells are not uniform in size and shape. Okay? And dysplasia is thought to be precancerous. It doesn't have to continue to form a tumor, but it can. Okay? So dysplasia is a result of persistent injury, but it's not adaptive like metaplasia was. So this picture is actually dysplasia of the cervix. Okay, so you notice that this area of tissue is much larger and has greater cellularity than the tissue surrounding it. So the healthy tissue is a single layer of epithelial cells. The area of dysplasia is this much larger area with lots and lots of cells. Okay, so normally if dysplasia is discovered anywhere, whether it's on the skin or in the cervix, it's normally removed. So it can't have an opportunity to continue to, it doesn't have an opportunity to form a true tumor. All right. Oh, and so here's a good look at metaplasia of the tracheal epithelium in a smoker. So we've got this nice, lovely columnar epithelial, ciliated columnar cells, and then replacing that are just simple squamous cells. Okay. And as I said, that's reversible. Metaplasia is reversible. Oh, here's another dysplasia. Was that other one? Oh no, that was metaplasia. Sorry. Anyway, cervical dysplasia. Here's a picture of cervical dysplasia, and the margin of dysplasia is the more darkly colored area versus where you see more white space is normal cervical tissue. So you can see that the darker color reflects this greater cellularity. There are more cells, more nuclei that are causing the color to get darker. And then the normal area, you see the interior of the cells and that white space. Okay. Yes, ma'am. Maybe. Mm-hmm. No, so the cells in metaplasia are they're behaving, right? So they're not overly mitotically active. They are going if I go back to one slide, the replacement of the ciliated columnar with the simple squamous, they look like simple squamous should look, right? They're not what's supposed to be there, but what's there has a normal appearance, if that makes sense. So basically what this means is, so I use the word replaced, but it's maybe not the right word. So when you look at the tissue, instead of seeing the terminally differentiated cell type, you see a less differentiated cell. So the cells are not getting an opportunity, or they're just not differentiating to the terminal cell. They're staying, so this might be simple squamous, this might be columnar unciliated, right? So instead of getting here, they're just stopping here. Does that make sense? Yes, ma'am.
Next question, in the next photograph of the cervix, how would you be able to tell that the left side isn't cells that are atrophied rather than the right side being dysplasia?
Pathologists go to school for a really long time to be able to identify tissue. Yeah. It's a real art to be able to identify. But it's a good question. All right. Okay, so other manifestations of cell injury, other things that we see when cells get injured, accumulations or infiltrations. An infiltration or an accumulation is when the cell starts to increase its intracellular storage of something, okay? And sometimes the something that it's storing is not something it normally should store. Okay, so for example, when you see people who have chronic exposure to combustion, so chronic exposure to soot, right? Firefighters or something like that. What you'll see is that in the epithelial cells of their airways, you'll actually see sometimes soot accumulations inside of the cell. Okay. Now, what infiltrations or accumulations represent is either the cell is presented with something it can't digest, and so it just walls it off, right, to protect the cell, or the ability to digest something is impaired or overwhelmed. Okay? So these accumulations or infiltrations are sometimes the cell's ability to manage a substance that it cannot digest, or a substance that it should be able to digest, but they have like a deficiency or impaired digestion, or it should be able to digest this thing and it's just overwhelmed by how much of it has. So let's look at an example of this. So here we've got an image of brain tissue of an individual with a disease called Tay-Sachs disease. And Tay-Sachs disease, people have an enzyme deficiency in a very specific enzyme that breaks down lipids. Okay, and as a result, what the arrows are pointing to are these vacuoles of lipids that are inside of the neuronal cells in the brain. So because the cells are missing this enzyme, the best they can do is just accumulate this particular kind of lipid into a vacuole. And of course, the presence of the vacuoles in the cells impairs cell function, and it leads to change in function of the brain. Another example of infiltrations or abnormal accumulations is fatty liver disease. And this is a really good example because there are several causes of fatty liver disease. So with fatty liver disease, normally the liver does have intracellular storage of fat. That's normal. But with fatty liver disease, intracellular storage of fat is amplified dramatically. Okay? So you can see these big white circles in the top picture are just big lipid vacuoles inside of these liver cells. And then in the bottom corner, you see the gross anatomy of the liver has changed. So the liver is normally this like lovely rust-colored organ, but this liver is actually almost orange or yellow, right, from all the fat that's contained in it. And it's often enlarged as a result of the fat accumulation. So a couple of things that can cause fatty liver disease. One is something called alcoholic hepatitis. Okay, so hepatitis means inflammation of the liver, and when alcohol abuse is the cause of the inflammation of the liver, it will appear with this fatty liver appearance. Okay? So the liver metabolizes ethanol. It metabolizes alcohol, and it produces as a byproduct a substance called acetaldehyde. And acetaldehyde is highly toxic to the liver, and it impairs lipid metabolism. So when the liver is forced to metabolize alcohol constantly, it produces too much of this acetaldehyde, and it impairs liver digestion, liver fat digestion. Okay? And you get this fat accumulation, which is reversible. Okay, it is reversible. Another cause of fatty liver disease, I'm dating myself because this is, I've been talking about this movie for a long time. Super Size Me, anybody ever seen that movie? Yeah, so that movie actually was when I was in graduate school, a long time. So the guy ate nothing but McDonald's, right, for a month. And then by the end of the month, he actually had impaired liver enzymes. And he had fatty liver disease. Yes, ma'am.
I was just going to say that the projection is not. I didn't know that.
Oh, that's weird.
Good job.
Thank you.
How long had it been on?
Was it had it just done? Okay.
Oh.
It's coming up.
Okay.
So Amphitheater 7 apparently hates us as much as we hate it. All right, it's warming up. Thank you for telling me. So yeah, Super Size Me. So he ate nothing but McDonald's for a month, very, very high fat diet, and he just overwhelmed his liver with fat. So the result of those 30 days was that he basically had fatty liver disease that was reversed once he went back to his normal diet. But he had abnormal liver function, elevated liver enzymes. I mean, he basically had the liver of a alcoholic as a result of eating nothing but McDonald's for a month. Okay. Another example that will definitely stick in your brain is foie gras. Right? Anybody ever have foie gras? So I've never had it because I'm afraid I'm going to like it. I don't like liver, so I probably won't. But basically, it's fatty goose liver. And the classic way of producing, this is why I don't have it, because I think it's a little cruel, more than a little cruel. The classic way of producing this fatty goose liver is by force-feeding geese a very high-fat diet. And basically it induces this fatty liver disease that is apparently delicious. But so I saw a hand. I'm not sure who it was. Yeah.
Does it take a month, or how long does it take for alcohol to cause fatty liver disease versus the man who is in super size?
How long does it take alcohol? It really depends on how much drinking you're talking about, right? So really, really severe drinking of like hard liquor constantly won't take very long.
Because there are alcoholics who start their morning with whiskey, and how soon into that kind of lifestyle involved?
So the liver is an incredibly resilient organ, and it really depends on how much rest the liver gets. So the liver with enough rest can correct itself, but if there's not enough rest, the damage will accumulate. But I mean, it really depends on a lot of things. But some people can go a really long time of really hard drinking, and some people can't. It's very individual. Yeah. Yes, sir. Fatty liver disease, when it's what I'm describing, the alcoholic hepatitis, is happening well before the onset of cirrhosis. So cirrhosis is basically scarring of the liver. Cirrhosis is not reversible. But hepatitis, this kind of hepatitis, it can be reversed with cessation of drinking. Yeah. Yes?
Where the liver, you said it's reversible, is that what we should be able to reversible, or like the slide before brain, is that also?
The Tay-Sachs slide is not reversible because it's an actual enzyme deficiency. So it really depends on, I mean, if the enzyme could somehow be replaced, I'm not sure if that's possible with Tay-Sachs, then that maybe. But, yeah. Yeah, I mean, so many of these manifestations of cell injury are reversible, but the liver is particularly resilient because it has such amazing regenerative properties. Yeah. Okay. So this is an example of infiltrations or accumulations as a manifestation of cell injury. Hydropic swelling or water accumulations, it is a manifestation of cell injury, but normally with hydropic swelling or water accumulation in the cell, we talked about this with hypoxic injury, there is a point of no return. Okay, so in the top slide, we have a needle biopsy, liver biopsy, and what we see in the center is this zone of white space, right? This is a zone of basically dead cells that are really swollen and bloated. Okay, those cells are not going to recover. Those cells are dead. If we look underneath that, we see using electron microscopy, we can actually see organelles within a cell. And on the left side, this is what a healthy inside of a cell should look like. Okay, the flat discs is endoplasmic reticuli. Okay, and then the circles are mitochondria. And you can kind of see within the circles the folds of the mitochondria where the electron transport chain happens. The picture next to it is hydropic swelling of the organelles. You see the big white spaces are those endoplasmic reticuli enlarging and swelling with water. You see the mitochondria swelling. When you get this kind of swelling inside of those organelles, the cell is not going to recover. The cell is going to die. Okay? And when this kind of cell death happens, we call it coagulative necrosis. Okay? So necrosis is death of tissue. And if we look at the next slide, it's just more of this comparing normal mitochondria to swollen, never going to work again mitochondria. Okay? And, yes?
So necrosis compared to like apoptosis. So necrosis is the tissue, apoptosis.
We'll talk about that in a second. So when cells die in this way as a result of injury, when cells die in this way, the reason why we call it coagulative necrosis is that release of lysosomal enzymes I mentioned earlier, it's going to cause coagulation of proteins in the cell. Okay, and denaturing of proteins in the cell. Okay. So necrosis is cell death as a result of injury. Okay. And the term coagulative refers to that autodigestion that happens as a part of that cell death. So the lysosome explodes, and those digestive enzymes just eat the cell itself. Okay? So this is irreversible cell injury or cell death. Okay? So when the cell dies as a result of these injuries, we call this necrosis, and the generic term for it is coagulative necrosis. Okay? And normally necrosis is a term to describe tissue death. Okay? So an individual cell death, when you have a collection of cells dying, that's tissue death. Okay? Now, we have other terms to describe this kind of tissue death, depending on what tissue type it happens in and what it looks like. Okay? So coagulative necrosis is a fairly generic term. There's what's called liquefactive necrosis, which is exactly what it sounds like. The tissue liquefies. Okay? And we'll look at that in a moment. We have caseous necrosis and fat necrosis. Okay, so let's look at generic cell injury. When a cell dies, what is it going to look like? Now, this is a cell death from injury. Okay? Apoptosis is programmed cell death. Apoptosis looks nothing like this. Okay? This kind of cell death looks like the cell is exploding. Okay? It gets bloated and it looks like it's exploding. Apoptosis, the cell looks like it's imploding. It gets smaller and it looks like it's collapsing in on itself. So, some of the things we see in this picture, number one, we see the cytoskeleton is denaturing. All this protein in the cytoskeleton is denaturing and coagulating, okay, and clumping together, which is why the cell loses its nice normal shape. Okay? It's now an amorphous mess. You have swelling of the cell. You have swelling of the organelles. Okay? You've got ribosomes that are misshapen and floating around. And you've got a nucleus that is abnormal in appearance. Okay? And the nucleus of the cell is going to, at first, the nucleus shrinks, kind of collapses. Okay? And that's that top picture. And then, as time goes by, the nucleus looks like it's just scattering. Okay? It's just disintegrating. And then finally, the cell looks like it has no nucleus. Okay. So with necrosis, the cell looks like it's bloated. It looks like the nucleus is shrinking and breaking apart, and then finally dissolving. So this is a band of coagulative necrosis in cardiac tissue. Okay? A band of coagulative necrosis in cardiac tissue. So this is actually what an area of infarcted tissue. This is what an area that is dead as a result of a heart attack looks like immediately after the heart attack. Okay? The cells, if you notice, they are darker in color, and if you notice, there is less white space around them. Right? There is less white space around those cells in that band, and that is reflects that swelling of the cell. Okay. Now, when this heart tissue undergoes healing, it's not going to be able to replace those muscle cells with new muscle. Okay? What it's going to do is just replace that those muscle cells with scar tissue. Okay? But immediately after an infarction, the cells are bloated and swollen and dead. When necrosis occurs in tissue with little to no connective tissue, when necrosis happens in tissue that has almost no connective tissue, like the central nervous system, it undergoes what's called liquefactive necrosis. Okay? So once those cells die, there's really nothing keeping the tissue together. So it looks like that tissue just kind of liquefies. And you can see that in this picture. It just looks like there's a area of tissue missing. Okay. Sometimes it will look like a cyst, where the fluid will just be walled off with a membrane, right? And it just looks like a cyst. So that's necrosis in tissue with very little connective tissue. Okay. When you get necrosis in organs that have high fat content, okay, or high fat deposits, okay, breast tissue, pancreatic tissue, there's lots of fat deposits in those tissues. You get something called fat necrosis. And there's a strange thing that happens where as those fat cells die, the fatty acids leak out of the cell. They combine with ions in the intracellular and extracellular fluid, and they actually form soap deposits. Okay? They actually form calcium soap deposits, which, if you look at this area of fat tissue, it has kind of a hazy appearance, right? That's what those soapy deposits look like. Okay, so that's fat necrosis. And so, like I said, that happens in organs like breast tissue or pancreatic tissue where you have high fat content. Caseous necrosis or caseous necrosis, the term casein refers to cheese. And caseous necrosis is a necrotic tissue that has kind of the appearance of cottage cheese. Yeah. So this kind of necrosis happens in tissue with a moderate amount of connective tissue. Okay. So there's not enough connective tissue to keep the tissue together, but there's enough to prevent it from completely liquefying. Okay? So it takes on this sort of clumpy cottage cheese appearance. So a really common example of where we see caseous necrosis is in lymph nodes of the lungs when people have tuberculosis. The pathogen of tuberculosis tends to infect immune cells, and those immune cells are found in those lymph nodes. And so you end up with this necrotic tissue in the lymph nodes. And this is a picture of an actual pulmonary caseous necrosis with TB. Yeah. Yeah.
So because TB forms really, really slowly, would that also form really slowly? Because, I mean, because it divides like one cell every 24 hours, so would that also take a long time?
It would take a while to get to a necrotic lymph node stage, yeah. Yeah. Okay. So the last form of cell death that we're going to talk about is apoptosis. And apoptosis is a very, very different form of cell death than necrosis, essentially, than tissue necrosis. Necrotic cell death is, like I said, because of an injury. Okay? And the injury is causes irreversible damage. The cell can't sustain itself, and it dies. With apoptosis, every cell in our body, within its genome, it has a program that initiates cell death, that can initiate apoptosis. Now, cells in our body are not people, right? Cells in our body are cells. And cells are actually designed to eliminate themselves if certain signals come up, which suggests that the cell may become a danger to the organism as a whole. Okay? So some of the reasons why apoptosis can get triggered is if we have proteins that cruise around the nucleus looking for errors on DNA. Okay? And if they find enough errors, if they find lots and lots of errors or mutations along the DNA, they will trigger this apoptosis. Okay? Because the cell is trying to prevent itself from becoming a cancerous cell. So apoptosis is something that must be triggered. It's a gene that must be transcribed and expressed. And then basically that gene codes for proteins that go in and just start chopping up the genome. Okay? And when a cell is undergoing apoptosis, it looks like it is collapsing in on itself. Okay? It actually shrinks. It forms all of these vesicles called apoptotic bodies, and then those apoptotic bodies they lyse, or sometimes they get phagocytized by immune cells. Looks nothing like necrotic cell death. So some of the things that can trigger this programmed cell death, as I said, DNA damage, when the cell detects a certain degree of DNA damage, viral infection, certain kinds of membrane damage or mitochondrial damage, certain forms of cell stress, particularly within the endoplasmic reticulum, and then immune cells can trigger apoptosis. Okay. So an immune cell can notice that a cell is cancerous, or infected with a virus, and it can trigger it to induce it to trigger apoptosis. Okay. So apoptosis is a natural function of cells. This programmed cell death is a natural function of cells, but an organ or a tissue may get triggered to, lots of cells may get triggered to perform apoptosis as a result of some injury, okay? Like a viral infection or something like that. Now, apoptosis, while it sounds dramatic and it sounds so self-sacrificing by ourselves, apoptosis, if we block apoptosis, that is super bad. That is not good, okay? There are cancers that develop because of their ability to block the apoptotic process, okay? So apoptosis is actually a positive mechanism in the body. So as you can see, whether tissue or cells are faced with chronic stress and change their shape, right, and therefore their function, or persistent injury or acute injury causes cell death, it will change the function of the tissue and the function of the organ. And that's where clinical manifestations come from, okay? When an organ functions differently, it contributes to the entire system differently, and then we start to see signs and symptoms of disease, okay? So that's kind of the basic idea with this cellular basis of disease, that injury starts at the cellular level, it changes tissue function, organ function, and then we start to see signs and symptoms of disease. I saw somebody's hand up here. No? Okay. So let's move to the next section, the nervous system. Oh, I can't. Damn. Yeah. All right. Well, we have a nervous system, and that's about all I can say. So I will say that the idea behind the idea behind us talking about the nervous system, we are going to talk about 3 systems in the next few weeks. That it is an attempt to understand how the body controls itself and functions on a more global level, okay? So we're going to learn about the nervous system, the normal function of the nervous system and the endocrine system, because those 2 systems are our major control systems. They control and coordinate all functions in the body, okay? So we're not going to get into diseases of those 2 systems until next semester, but we are going to learn about normal function of those systems. And then we get into the immune system, because we have to understand immune function. It underlies a lot of development of diseases that we talk about later. And we will talk about diseases of the immune system within that unit. Okay? So we'll start that nervous system lecture next week. But there is a nervous system topic for you to watch this week and take that quiz. Okay?
We don't get 2 chances.
Yeah, and there's no 2 attempts on the quiz. Okay, it's 1 attempt. So make sure you're ready to take it when you take it. Thank you. Have a good week, guys.